Welcome everyone to our GIA Knowledge Sessions. These are a series of talks and seminars about gemology that are fueled by our decades of research. And it's our mission to share all of our discoveries and learnings with the world. So I'm very excited to kick things off today. I'm Kelly Giordano, a member of the content team here at GIA. And I'm joined by Wim Vertriest, supervisor of field gemology. And he's going to tell us all about the natural processes that form colored stones. So before we get started, just a bit of housekeeping. Everyone attending this is automatically on mute. So if you have a question, please submit it using the Q&A feature at the bottom of your screen. There will be a Q&A session at the end where we'll have the opportunity to answer some of your questions, and feel free to ask questions as we go. We'll also send a recording of this session to you later today, and that message will also include a survey, so we'd love to get your feedback. And so with that, I'm going to pass it over to Wim.
Hi, good morning, everyone. Thanks for the introduction, and I'd like to thank everyone for attending today. This is going to be a very exciting seminar for me, mainly because this is a topic that I'm personally very interested in. Plus, it's a topic that's not very well known. I mean, there's a lot of colored gemstone geology that we don't understand, and it is extremely complicated. But I just want to share some of the current state of knowledge with every one of you. And I try to bring it down to a level so that it's understandable for people who do not have an advanced geology degree. So we're going to really build this up slowly. I'm going to try to explain all the terminology at a level that everyone can hopefully understand. And that will make you appreciate a little bit more the gemstones that we are handling, that we are seeing every day in our life, and that we are privileged to work with, and how they form, and how those processes that they are formed in are really spectacular and are really unique. So how these treasures of nature, why they are so unique, we'll try and go a little bit more in detail on that topic today. So the first thing I want to address is, where do we actually find gems? You find gems in a lot of environments, but that is not always related to the geology. So of course, it would be amazing if we can find gemstones in places like this, where we dig a tunnel and it glitters and sparkles everywhere because of these shiny gemstones. Unfortunately, this only happens in Disney movies. The real world is a little bit more challenging, a little bit more difficult. So for deposits where we find gemstones in the real world, we separate it in two categories. And the first one that we call is what we call primary deposits. A primary deposit is where you find a gem in the rock where it was formed. So basically your gem is growing, and it is growing in a rock, and you find it like that. That rock could be weathered. With weathered, we mean completely broken down by natural processes, turned into clay and dust, but it's still there, and the gemstone is still inside. But in most cases, it is still hard rock like we see it everywhere around us. So it takes a lot of effort to mine it. Now, when you have a primary deposit, you very often have a low to medium concentration of gemstones. That means that you have gemstones scattered all throughout the rock. But it also means that you have all different quality grades scattered throughout the rock. You have your super high quality crystal clear gems in there, but you also have your smaller off-colored, very fractured, very included gems, because they haven't been moved from that rock. Plus, on top of that, a lot of hard rock is difficult to mine. With difficult to mine, we mean you often need a lot of energy to get the gems out of it. Like here on the photo, you see some emerald miners in Zambia that are using manual labor with picks and hammers to break the emeralds out of the host rock. Why don't you do it at big scale? Because of course you have to be careful if you use heavy equipment, if you use things like explosives or blasting. You want to break the hard rock, but you don't want to break your gemstones. And finding that balance is what makes hard rock mining so extremely difficult. Now, of course, for some gems, we have to make that exercise, and we have to mine them from primary rocks. And those are typically gems that are a bit more fragile. Colored gemstones like emeralds that often have abundant fractures, or things like tsavorite or tanzanite, stones that have a lot of cleavage. Now, of course, while it is more challenging to mine these deposits, it has the advantage that you get a very good understanding of the local geology and the processes that form it, because you're looking right at it. You're looking at the rock that formed the gemstone, so you really get a good understanding of it. Now, these are two other examples. Here on the left, we see a photo from the Pala mine in the San Diego County in California, where a miner is extracting a large spodumene crystal. You see that the rock around it is completely turned to mud, but it is still the original rock where it formed. It has just been weathered to rock and that soft sand. But the spodumene crystal you see in there is still beautifully intact and can be extracted by the miner. Another example on the right, we see here the tunnels through the hard rock, the hard marble in Mogok, Myanmar, where people are mining rubies directly from that marble. It is a very labor-intensive process where people have to move very carefully, drill the marble, blast it out, check if there's rubies in there. Because if you go too fast, if you go too extreme, if you put too much energy in there, you will not only break the marble, but you will also break up the rubies. So that's the first type of deposit, what we call the primary deposit. Very closely, very intimately related with the local geology, with the formation geology. So a good understanding of what actually formed your gemstones in these environments. Now, the other type of environment is what we call a secondary deposit. A secondary deposit means that your gems are weathered out of their formation rock. When rocks are exposed to the surface, they are submitted to weather conditions. There's rain, there's wind, there's water, and over time they break down. Now, as we all know, gems are durable by nature. That is in the very definition of a gemstone. So they will survive most of that process. So your gemstones are what's left over from your rock that is completely turned to sand, to clay, to dust. And all that sand and clay and dust is moved away, but your gems are surviving. And those gems are transported either by gravity, so basically rolling down the hill, or in a mudslide. But most often they are transported by water. Water is a very fluid medium, holds a lot of energy, has a lot of potential to move your gemstones. So in rivers or even beaches, that's where you can find a lot of the secondary deposits. So when you have a secondary deposit, it has some advantage that your gems are already concentrated by natural forces. So all those gems that were spread out in that original host rock are now concentrated by the water. The water or the gravity brings them all together and piles them up. Not only do you get a higher concentration of gemstones, you also get higher grades of gemstones. Why is that? Because if you have stones with fractures, stones that are a bit smaller, they simply won't survive that transport. When you keep hitting those, when they're moving in a river, those stones keep hitting each other. They get banged against rocks for hundreds, for thousands, for 10,000, for 100,000 of years. And of course, only the strongest will survive that. So stones that have a tendency to cleave, or stones that have a lot of fractures, will simply be ground up in that process. But then probably what is most relevant for us is that those deposits are a lot easier to mine. What easier to mine is you often don't need explosives or heavy equipment or drilling to get access to them, because you find them in loose sediments, gravel layers, sand layers around your riverbeds, maybe old riverbeds, maybe recent riverbeds. So let's look at so the stones that survive this process are concentrated in loose gravels, only the higher grade, making it very easy to extract a lot of gemstones. Now, gems that we typically see in this kind of deposit are the tougher gems, gems that are able to survive this transport. Diamond is the prime example, but diamond is not a colored stone, so we'll focus on some other ones. But a stone like corundum or spinel with high hardness, no tendency to cleave, several of the garnet varieties as well, they are often mined from these secondary deposits. Now, of course, if you have a secondary deposit, it means that your gem was weathered out of the host rock and it has been transported, so you don't have any physical contact. You don't really know in what kind of environment this gem originally formed. So that makes it very challenging to understand the geology that formed these gemstones, because the gemstones locality where you find them is completely detached from the place that formed them. And this is an example of one of those secondary deposits related to a river. This is a very recent deposit in Pailin, Cambodia, where rubies and sapphires get washed down from the river. So the river comes from the Cardamom Mountains that you see in the back here. And every year in the rainy season, this entire area floods and brings in new gravel. That river holds a lot of energy, is able to move large boulders. Like you see in front of this man, these are boulders sometimes that are up to a meter big. So it's really a lot of energy in that river. And that river is bringing up new rubies and sapphires every time. So every year, this miner can go back to the same spot and look for rubies and sapphires that were washed in there by the river. Another example of a secondary deposit is an older deposit. This is the Mozambican ruby mines, where this whole body of rock that held the rubies was weathered down into a very thin layer. So the only thing that's left of that massive body of rock is here, this layer with all these white specks. So there's big quartz boulders, there's the rubies that are left as well. So all of that is concentrated in a layer of 30 centimeters that is now being mined for the rubies. And you can see here that some artisanal miners had built a shaft to reach it, but they had abandoned it when a larger operation came along. So just to make a quick comparison, we've got primary deposits and secondary deposits. So a primary deposit is where gems are found in the rock where they were formed. A secondary deposit is where gems were removed from the rock where they formed, and usually only tougher gems will survive this. If you want to mine a primary deposit, it is very energy intensive, very hard, while mining is fairly easy in most secondary deposits, especially when you compare it to primary deposit, because no mining is easy. In primary deposit, there's no natural concentration, no sorting of gems, while in secondary deposit, nature has done some of the work for you. It has concentrated gems, it has sorted them by quality, you could even say, because the lower grade material has simply not survived that process. Now, the one good advantage that you have of primary deposits is that the geology, the formation history of those gemstones is way better understood. It is often better documented because people need to understand it to advance their mine and where to look for those gems, where to direct the energy that you're going to invest in mining those gemstones. While in secondary deposits, the geology that actually formed the gemstones is not at all or very little understood. So that makes it very challenging to find out how those gems really formed in the earth. So that's a quick reminder of where we actually find gems. And now we'll go a little bit into the geology of gems. So first we'll start with a little bit of terminology. This is a geology crash course that we're going to go through really quick. But some of these terms are going to be very helpful to understand the later explanations when we're focusing on corundum and emerald formation. So I think the first thing we need to address, this is really, that's something that almost everyone is familiar with, is the rock cycle. So basically, if we start very deep in the earth, all the rocks start as a magmatic rock, magma molten. So all this molten rock, and from this soup, you can crystallize some rocks. That is what we call igneous rocks. Now, of course, over time, when they get exposed to the surface, you weather them down, they get turned into very fine grains. That is what we call sediments. Sediments can be really small, they can be bigger, but it's basically loose pieces that are all thrown together on a pile. Now, if you start burying those again and you start compacting them and really solidifying them, you have what we get a sedimentary rock. That you can see an example here on the right where we have a sedimentary rock buildup of fragments of living organisms, shells, and stuff like that. When they're compacted together, they form a sedimentary rock. Now, if we bury these even deeper and we apply a lot of heat and pressure to it, we get what we call a metamorphic rock. So metamorphic rocks have often seen a very turbulent history, very dramatic changes in mineralogy because they've been subjected to a lot of pressure, a lot of heat, giving these beautiful patterns where you can just see that this rock has really been smashed together and has been subjected to incredible forces deep within the earth. So now you have an understanding of how rocks basically, how the different types relate to each other. Now let's look a little bit more in focus when we look at what actually a mineral is. Now there is no real definition of a mineral, but the more or less the 5 points that everyone agrees on is that a mineral has to be naturally occurring. You can grow a mineral in a lab, for example, lab-grown diamonds or synthetic corundum, but those have a natural counterpart that is exactly the same. So we still consider that a mineral. Something that is only grown in a lab, we do not really consider a mineral. A mineral is not biogenic. With not biogenic, not organic is basically what we mean. Plus, it also has to be a solid at room temperature, but that is also something that is a little bit under discussion. But the two most important parts are a mineral has an ordered internal structure and a mineral has a definite chemical composition, which means that you can draw a structure that is repeated in infinity by this mineral, and a definite chemical composition, which means that you can write down a chemical formula for your mineral. You can have very easy and very simple minerals like diamond, which has a definite chemical composition exclusively of carbon, and the crystal structure is fairly simple, like we can see on top. Like the one on the bottom is a lot more complex, and also that definite chemical composition is a lot more complex. This is lidocotite tourmaline, but you can see that it still has this definite chemical composition. So that is what a mineral is. Now, what really is rocks, minerals, crystals? How do these things relate to each other? So a rock is basically an aggregate of one or different minerals. If you form different minerals together, they form a rock. Sometimes it's only one mineral, still can consider a rock. Now, some gems are rocks. For example, mausitzit, which is commonly used as a jade imitation, is often used, is actually a rock. But probably the example that most people are familiar with is lapis lazuli. Lapis lazuli, which consists of the blue component, but you also have the white specks, which are calcite. You have the golden specks, which are pyrite. So it's an aggregate of different minerals, so a rock. Of course, you have also gems that are not considered a mineral. Opal is not considered a mineral because it doesn't have that fixed structure. Amber is not considered a mineral because it is biogenic. It is produced from the resin of fossilized trees. Now, what really is a crystal? A crystal is any solid with an ordered internal structure. So it doesn't have to be naturally occurring. It can be organic. But all minerals form as crystals, but not all crystals are minerals, for example. Now, if we look at how to form minerals, which is important for what we're going to discuss, because this is basically what we're going to discuss for corundum and beryl in a few minutes. The first thing you need to know about mineral growth is that you need the right chemical conditions. Is there water present or is there no water presence? What's the pH, the acidity of the environment? What is the oxygen level of the environment? That's all important. But the most important thing is the availability of elements. Which ingredients do you have to build your minerals with? And availability is something else than presence. Sometimes you have minerals presence, but they're simply not available because they're already locked in a different mineral. So the availability of elements is really critical when you build minerals and gemstones. So we can compare that with the ingredients that you need to build your mineral. Now, the other thing that we need is the right physical conditions. We need to be at the right pressure, at the right temperature, and also we need time to grow those crystals. And probably the best example are these three different minerals. They have the exact same chemical composition, but depending on the pressure and temperature where they form as very different minerals. So you can basically compare this to your oven settings. How hot and how long do I have to cook this before I get the perfect dish? Now, of course, we have the ingredients, we have the right oven settings, but we have to remind this quote from John Koivula. He said that Mother Nature cooks in a dirty kitchen. Nothing ever goes like the perfect recipe. It is a little bit too hot, it is a little bit too cold. You put a bit too much of this and that, there's not exactly enough of this. So you always have modifications, so nothing ever goes perfect in there. It's Mother Nature, she cooks in a dirty kitchen. It's not a clean lab that we're working in. Now, something else that I want to bring up real quick, and this is maybe a little bit more complicated, is the composition of the Earth's crust. The Earth's crust, where most of our colored gemstones form. But you see that the majority of the crust actually consists of oxygen. Almost half of it is oxygen. And then you see that the other dominant elements are silicon, more or less a little bit over a quarter, aluminum a little under 10%, and then a few other big ones. But the vast majority of elements that we know from the periodic table are actually extremely rare in the Earth's crust. And that is going to be important for some of our mineral formations, for some of our gem formation. Now, of course, we know that when we look at the Earth, those elements don't appear as their simple elements. You don't just find oxygen in the crust. All of these elements are locked in minerals. And the mineral composition of the Earth is, especially the Earth's crust, is dominated by what we call silicate minerals. Silicate minerals like feldsparts, which consist more or less half of the crust where we form our colored gemstones. You have a significant part of quartz, then you have some what we call chain silicates, inosilicates like amphiboles and pyroxenes. We have micas, clays, other silicates of more unusual types, but only 8% of our gems are not of our minerals in the crust are considered non-silicates. So what actually is a silicate? A silicate mineral is a mineral that contains a silica oxygen tetrahedra. So it looks a bit like this, with your silica in the middle and your oxygen atoms. But you have in all their possible combinations. So this is your basic building block, but you can let your fantasy run wild and combine them in any way possible. And these are just a few examples. You can keep them as they are. You can put two of them together. You can make a circle out of them. You can make a chain out of them. You can make two chains and put them together. You can make a 3D framework out of them. All of that works for silicate minerals. Now the 8% of minerals in the crust that are not silicates, they belong to these families. So the first one that we have are native elements. For example, diamond, which is just pure carbon. There's no silica involved there. We have sulfides. Sulfides are minerals that have a significant sulfur component. For example, pyrite, which is iron sulfide. The other ones are what we call halides with a fluor, chlorine, or bromine ion. And I think the best example from the gem world that we know is fluorite, but the most common mineral that we know from this family is probably halide, also known as kitchen salt. We also have the oxides and the hydroxides, so minerals that have a strong oxygen group or a hydroxyl group. And this includes minerals like corundum, which is aluminum oxide, and spinel, which is magnesium aluminum oxide, which are of course very important gemstones. But we also have the carbonates, calcite, dolomite, aragonite. They typically have those carbonate groups, so that CO3 group combined with some other elements like calcium or magnesium. And then we have a few other ones like borates, where we have a boron atom, sulfates, phosphates, but they're not super important for what we're going to discuss today. Plus, it gets really complicated there. Now, a last concept for the geology crash course that I want to introduce is plate tectonics, the moving earth. So I think most of you are familiar with this concept, and that's basically that the crust of the earth consists of different plates. They're floating on a liquid, they're floating around and they bump into each other. And there's different modes that they can interact with each other. Like you see, for example, here in the Indian Ocean, you have two plates that are spreading apart. But in a lot of places, you have plates that come together. For example, here in South America, from the coast of Chile and a lot of the countries on the west side of South America, is where you have two plates coming together. And where you have them coming together, that's what we call active margins. That's where something is happening, and where something is happening, we want to know what. So these are two examples of active margins. You have two types of plates, basically what we call continental and an oceanic. And your oceanic plate is denser, heavier than your continental. So it has a tendency to dive under your continental plate because your continental plate is a little lighter and will stay on top, while your oceanic plate will be forced down because it's heavier. Very interesting from a geologic perspective, lots of volcanic activity, ore deposits forming there. But really for gemstone deposits, we're looking more where there's continental crust hitting continental crust. So two things that have the same density, there isn't one going on top of the other, they just hit each other, and the only way they can go is up. So they just crumple up, and inside that zone where those two plates come in contact, that is where we generate a lot of pressure, a lot of heat, a lot of interesting elemental interactions, and that is where we grow most of the colored gemstones that we're seeing. So now that we've all got a reminder of our geology crash course, let's take a look at the first gemstone. So the first gemstone I want to discuss is corundum. Of course, we know corundum as ruby and sapphire, but I'm going to take these two together because they're the same mineral, corundum. So what is corundum? What is ruby and sapphire? It is aluminum oxide. 2 parts aluminum, 3 parts oxygen. Extremely simple recipe at first sight. Shouldn't be too hard to build this. Of course, we need to give it some color. For ruby, we need chromium to create the red color. For blue sapphire, we need iron and titanium, but that shouldn't be an issue either. So if we look at it, we need oxygen, we need aluminum. Oxygen, nearly half of the crust consists of oxygen. Aluminum, 8% is there. How hard can it really be to form that corundum? As it turns out, actually pretty hard. Because as we've seen before, most of that oxygen and aluminum is already locked in all different minerals. Plagioclase, alkali feldspar, they contain a significant amount of aluminum. Pyroxene, amphibole, mica, clay, and the other silicates often contain a lot of aluminum as well. So a lot of that aluminum is actually incorporated in those silicates. So when you have silica around and around your aluminum, they will always form a mineral together, meaning that there's no aluminum left for you. So as long as there's free silica available, corundum cannot form. With free silica is not the same as silicate. You can form silicates around corundum, but you need silicates that have a lot of aluminum in them. So as long as there's aluminum that is not incorporated in those silicates, that excess of aluminum can be used to create corundum. Now, where in the Earth's crust do we have situations where we have available aluminum, which means a relatively low content of silica and a relatively high amount of aluminum? There's 3 environments I want to discuss really short. The first one is what we call amphibolites, the second one are marbles, and the third one are a very large group of magmatic rocks. So let's start with the first one. The first one is an amphibolite, but what is an amphibolite really? An amphibolite is a metamorphic rock. So it means that a rock that has been subjected to a lot of pressure and temperature, there's a lot of recrystallization, a lot of complex textures in there, but it's dominated by minerals with a relatively low silica content. Minerals like amphiboles mainly, that's why we call it an amphibolite, but also biotites, some feldspars. And we can see an example of an amphibolite on the right-hand side here, where we have a lot of these dark minerals, and the white minerals are the feldspar, but the dark minerals are the amphiboles and those biotite micas. Now, these rocks are often derived from what we call mafic rocks. Mafic rocks, very rich in magnesium, iron, that's why they're so dark. But they're also very often enriched a little bit in chromium. So there's some chromium around that we can use to build some interesting gemstones. For example, ruby. Now the protolith, which means that what this rock looked like before it was metamorphosed, can be magmatic, can be sedimentary. That is not really clear at this point. It has been through such a journey, been subjected to such pressures and temperatures that it's most of the time unrecognizable, especially with the knowledge that we have today and the level of knowledge that we are right now. Now, as I mentioned, this is often a very high-grade metamorphic rock with a formation and history that is extremely complex. Most of the times, it hasn't been subjected to incredible pressures and temperatures just once, but it's been subjected once, twice, again and again, and it's been refolded and faulted, and fluids have been through it. So it's very, very complex to really get the history of these rocks. Now, the exact formation process of how we grow corundum in these rocks is not fully understood. For example, we don't know what the influence of intrusions is, what the influence of the composition of the host rock is. Are there fluids involved? What are the exact pressures and temperatures that we grow this ruby, and what are the exact pressures and temperatures that this rock has been subjected to? Those are all still open questions right now. And why are those open questions? Because most of these rubies and amphibolites are fairly recent discoveries. So we simply haven't had the time yet to study those deposits in depth at academic level with really advanced instruments, but there's a lot of work being done on them right now. So a few examples of corundum and amphibolites are the rubies from Mozambique, which are extremely common, but were only discovered 10 years ago. Rubies from Madagascar, which have been around for, let's say, maybe 20 years. So still very, very recently discovered deposit. Same for Tanzania with the Winza deposit, which was discovered, I think, in 2007, 2008. So still very recent. Of course, the Greenland rubies have been known for a lot longer, and they have been studied, and we understand their development a lot better. But still, there's a lot of questions and a lot of interesting open questions to be answered about their formation history. Now, a few typical things that we see in this amphibole-related rubies is very obvious. I think everyone could have guessed this. Those are amphibole crystals. Crystals of amphibole, we see them a lot around the ruby in the rock that formed this ruby, but we also see them inside the ruby. And there's basically two typical appearances. We have like these more irregularly shaped, sometimes even like rice grain shaped greenish crystals. Sometimes they're these transparent elongated rods that are typical for an amphibole shape. So that's what typifies an amphibole related ruby. These inclusions are very common in all of those deposits. Now the second type I want to discuss is marble related deposits. Well, first of all, let's start with what is a marble. And before we want to ask the question, what is a marble? We need to ask the question, what is a limestone? A limestone is a sedimentary rock, and the technical terminology is it's composed of skeletal fragments of marine organisms. Most people call those shells. So you basically have shell components, either full shells broken up, ground into little pieces. And if you have difficulty imagining it, we can all dream away with this beautiful picture of a white sand beach in the tropic. Most often, these beaches are consisting completely of the skeletal fragments of marine organisms, of shells. So if you give these beaches enough time, bury them deep enough, they will turn into limestones. Of course, a limestone is not exclusively built of those shells, those carbonates. There's also some organic matter that is built there. You see this palm tree over there. Maybe it drops some leaves, that organic matter gets buried. Some marine organisms that live there, they get buried in there as well, providing a source of carbon, of organic matter, some phosphates. But you also get some sediments in there. It's never 100% pure calcium carbonate, never 100% pure shells. So you get some clays, some sediments. And in a lot of these environments, you have a fluctuating sea level, especially when you look at longer terms, what we call a geological time scale. So over terms of 100,000 years, you see the sea level go up and down and up and down. And of course, that has an effect on the minerals that are forming there. Like when you drop your sea level, you will have formation of what we call evaporites. I think it's all in the name. It is what is left over after your water has evaporated. This is very similar to what you see if you have a lot of carbonate in your water at home. A lot of your kettles, a lot of your cookware, a lot of your shower will have this white coating on them. That's technically an evaporite. So the same thing happens. But of course, if you do it with seawater, what you see mainly is salts, sulfates, things like that, that are also deposited in that environment. So you have this mix that is mainly composed of shells, organic marine organism shells, with a little bit of organic matter, some clays, some evaporites mixed in between. Now, if you put that through enough pressure and enough temperature, you will metamorphose it and you will have what we call a marble. So your marble will consist of carbonate minerals dominantly, but you also have what we call accessory minerals. That is what is left over from those evaporites, from that organic matter, from those clays and sediments. So those are the accessory minerals. But most of that marble is actually composed of those carbonates. And it is the purity of the carbonates that people are very interested in when they look at marble as an ornamental stone. So marble is a highly desired ornamental stone because it is so pure, it is so homogeneous. And even if it is heterogeneous, so if it has some texture differences, they're often aesthetically very pleasing, which makes it very interesting as an ornamental stone. That's why we see a lot of statues in marble. That's why we see a lot of bathrooms in marble. Now, of course, as gemologists, as geologists, we are mostly interested in what is different from that marble, those accessory phases. Because one of those accessory phases, one of those things that has, that comes from that organic matter, from those clays, from those evaporites, if you put enough heat and pressure on them, one of the things that you will form is this. So those heterogeneity, that is those accessory minerals. Some of those accessory minerals are corundum, beautifully red corundum, what we call ruby. So this is a beautiful example of a ruby, about 2.7 centimeters tall in a marble. So that's why we are interested in marbles from as gemologists. And this reminds me of a funny story that a friend of mine who lives in Vietnam, close to the ruby mines there. The rubies there are found in the marbles. But the marbles are relatively pure, so people are mining those marbles as ornamental stones. And he was hanging out with a few of those quarry operators, Italian guys who ran the original marble quarries in Italy that are now working in Vietnam. And those guys were complaining to him that their marble is all useless because there's too much corundum and too much spinel in there, and that makes their marble less desirable. I would personally pay a premium for a kitchen countertop that has rubies and spinel in them, but apparently the general market disagrees with me there. Now, if we go a little bit more technical and we look at how to form corundum in marble, we'll just go over the checklist real quick. So we have a marble dominantly consisting of calcium carbonate or magnesium carbonate, but there's no silica there. So we have that silica poor environment. There is no silica that can suck up the aluminum and build some other crystals with it. Now, even if you have that, you have your clays and your sediments that are a source of aluminum and chromium, but they're at a very low concentration. The aluminum is in a concentration of 1,000 parts per million. So if you take that marble and you break it down into little pieces, if you take 1 million pieces, only 1,000 will be aluminum. All the rest will be carbonate. And only 5 of those million will be chromium. So it's still scattered a lot, but it's mainly concentrated in certain bands where you form different minerals. Like here, we see a marble that has a lot of other minerals in there, micas, diopside, things like that. And that's our source of our aluminum, of our chromium. And there is where evaporites become into place, because these elements are all scattered around in that marble, but we need a medium to bring those together and grow those crystals. And that is where it has been shown that those evaporites, those salts that are present in those marbles, are very important. They play a role that they are able to mobilize the aluminum, they're able to move the aluminum from one side to the other, they're able to move that chromium from one side to another, and they bring that together so we can grow those beautiful aluminum oxide crystals, corundum crystals, with a little bit of chromium sprinkled in to give them a beautiful red color. So that's how we grow corundum in marble. Now, of course, typical inclusions that we see there are related to that marble. Calcite crystals are extremely common in this kind of rubies. They're the most common inclusion in, for example, rubies from Mogok, rubies from Vietnam, rubies from Afghanistan. Another typical inclusion that we see is what we call a fluid inclusion, or a negative crystal with a CO2 bubble there. Like a CO2 bubble, that just comes from the decomposition of those carbonate minerals, calcium carbonate. It has CO2 right there in the formula. So you get some CO2 in that environment as well. And that is trapped as these beautiful bubbles here in that Tajik ruby. Now the third type of corundum, I'm gonna take another sip of water because this is a heavy one and a complicated one. That is corundum related to magmatic rocks. So just a reminder, magmatic rocks, they come from molten rocks crystallizer. So you already have the intuitive feeling that we're dealing with very high temperature material here. And I want to point out that on the sketch on the right, you see a lot of different names and a lot of different forms of magmatic rocks. But the main difference I want to point out is that you have some of these magmatic rocks reaching the surface. That is what we call extrusive. So they appear on the surface as molten rocks. Those are the images that we typically know from Hawaii or Iceland of those volcanic eruptions there. But a lot of those magmatic rocks, they remain underground and they crystallize underground where they form these rocks. That is typically granite, and like the hallways in GIA Bangkok, they're all built of granite, so that's all magmatic rocks. But I think that's something that's very important, that we have those molten rocks reaching the surface, and sometimes they crystallize underground, but directly from those molten rocks. Now, of course, if we want them in relation with corundum, we still have that checklist where we don't want that free silica. So we need a lot of aluminum and a relatively low content of silica. Now, the first case is where we have corundum linked to magmatic rocks. So where your gems are found around the intrusion. I think you can all intuitively feel that when you intrude a rock with a molten rock, there's a lot of changes going to happen. I think something that's obvious is the temperature is going to rise around that intrusion. So that increased temperature, think back to what is necessary for growing a mineral. Maybe you already had the right ingredients, all the elements was there. There's no silica, there's a lot of aluminum, there's a little bit of chromium, but you just don't have your oven hot enough. You don't have the right conditions. And maybe that magmatic intrusion provides that extra heat, that extra push to grow your corundum crystals. Maybe you're in a different case, your magmatic intrusion can provide a new chemical balance in that system. Maybe it is able to take away some silica from the host rock. So that means that the relative content of aluminum becomes a little higher and your silica becomes lower. So some of your alumina is free to form aluminum oxide because your intrusion takes away the silica. Maybe your intrusion pumps in extra aluminum in the system, so aluminum oxide becomes stable. Those are all possibilities that are related to magmatic rocks. But most common, we see corundum inside the magmatic rock. So not around it, but inside. And again, here we have two types. I think the first type is where we have the corundum directly forming inside the magmatic rock. So you have this molten rock, and when it crystallizes, aluminum oxide is one of the phases that crystallizes. We don't really understand what this is happening. There's not a lot of these deposits known. Not most of those produce high gem quality material, but you can see that there's beautiful corundum, blue corundum crystals forming. In this example where we have a cyanide intrusion, which is a typical intrusion that has very low silica content, no quartz available, so aluminum would be stable. And the aluminum is associated with feldspars here, but you see this is a beautiful crystal of corundum with a nice blue color. But we don't really understand this process. We don't really know what the exact conditions are, and it's rather rare. What we do often see is a corundum as a xenocryst. What is a xenocryst? It literally translates to a foreign crystal, which means that your corundum is just a hitchhiker in the magmatic rock. It didn't form in the magmatic rock, it formed somewhere else, and while this magmatic rock was passing through, it picked up those corundums, and now we find them together. So the corundum did not form in that magmatic rock where it was found. So we find it in the surface in this type of rock, but it didn't grow in there. It was grown somewhere else. So it was mainly just a mode of transport. And I think people that are a bit familiar with diamond geology are very familiar with the term and the concept of xenocrysts, because most diamonds are actually xenocrysts. I think it is fairly safe to say that this is actually the most important geological environment for corundum in terms of gem sapphire volume. So a lot of sapphires are found in this kind of environment, and they're often referred to as the basaltic sapphire, as what we can see on the right here. This is a very old photo from an alkali basalt deposit in China, where you can see that this man is holding a piece of basalt with a xenocryst, here described as a megacryst because it is so big, of sapphire in that rock. And for those of you that still remember, this is one of those caps that they used on the top of the containers to keep your camera film in. So that gives you an idea of a scale of how big this corundum, this sapphire crystal actually is. But the sapphire crystal did not form in this hard rock, although we find it there. So this is just a sketch that I've adapted from an older publication to show you what the concept is. So in the first part here, we see that we grow ruby and sapphire somewhere in the crust. We don't know how, we don't know why, we don't know where, we don't know when. What we do know is it happened. Somewhere sapphire and ruby grew. Now a lot deeper than that is where we start developing this alkali basalt magma. So this molten rock that is developing, it's sitting there, it's moving, it's getting restless, and it starts its way up. It moves towards the surface. And when it moves towards the surface, it encounters these rubies, these sapphires, and it picks those up. Those are hitchhiking to the surface. So those corundum xenocrysts are moving up with that alkali basalt. And when it reaches the surface, this alkali basalt erupts, it flows over the surface, and it spreads out the rubies and sapphires that we find in there. So those rubies and sapphires were formed, unknown processes, very deep, but they were picked up by that basalt, and they're now found in that basalt. These are a few examples of corundum that we find in that alkali basalt. We have what we most commonly call the BJY sapphires, blue, green, yellow, which are very common in, like, I think all of the Australian sapphires. We find them a lot in West Africa, Nigeria, Cameroon, but also Southeast Asia. Thailand has multiple basalt-related deposits. Cambodia, southern Vietnam, China has a few of those as well. But those are randomly dispersed throughout the world. You even find some of those in Europe. Another stone that is famously found there is the black star sapphires. Opaque, black material, but with a beautiful golden star when polished correctly. And I think mostly famous from Thailand, but also found in southern Vietnam, in Australia. And then there's a few very special places in the world where we find rubies associated with those alkali basalts. And the most famous deposit is, of course, on the border of Thailand and Cambodia. But you also have a smaller deposit in Kenya. And there might be other deposits as well, but they're just not as known. They're not out there, and they're maybe not even discovered yet. So alkali basalts, extremely good environment to find rubies and sapphires, but they don't provide any indication for the formation of those sapphires, because they just act as a mode of transport from their condition from the place where the corundum grow. So just as a recap for this gem corundum, that gem corundum is aluminum oxide, and aluminum is actually very common in the crust. The problem is that it is rarely available, so you can't really build aluminum oxide with it. And that is because silicon always is going to pair with that aluminum to form silicate minerals. So you really need an environment that is very low on silicon, that is depleted in silicon. And those three environments that we most commonly encounter are amphibolites, which are metamorphic rocks with a relatively high aluminum silica ratio. There's still a lot of silica around there. There's just a little bit more aluminum available. Then you have the marbles, carbonate bodies. Silica is almost completely out of the picture. So what little aluminum is there can be used to build corundum in rare occasions. And then you have magmatic rocks, where you find stones either in the magmatic rocks, whether they formed there or are xenocrysts, or in the reaction zones around it. Very diverse environment, very complex processes. A lot of those are not even understood. In fact, most of those processes are poorly understood for the gem corundum. And I think that brings us back to what I opened the presentation with, and that is that a lot of the gem corundum is actually mined from secondary deposits, completely detached from the host rock, so no tangible link with the formation rocks, with the rocks that are actually causing the formation of that corundum. Now let's move to the next gemstone, beryl, and we're going to mainly focus on the variety emerald, because that's the most interesting gemology-wise, but also geology-wise. So emerald, it's a beryl. The beryl formula, we can see it here. It has beryllium, it has aluminum, it has silicon, it has oxygen. And it has chromium, vanadium, but we'll just discuss chromium here to give it that green color. So I think you can see, if you look at this diagram on the right again, you see oxygen, plenty of it available. Silicon, plenty of it available. Aluminum, plenty of it available. The main limitation that we have to grow beryl is the presence of beryllium. And beryllium is extremely rare. It is in that 1% right here. And it is actually so rare that we only find 2.8 parts per million of beryllium in the crust. That is 0.00028%. That is extremely rare. That is comparable to taking the entire city of Los Angeles and putting together one basketball team. So that's not a lot. That's very, very low concentration. Thankfully for us, beryllium tends to concentrate in certain environments. So do basketball players. If you're presented with that task, the first thing you would do is go to where you find the most basketball players. Those are the basketball courts, the basketball stadiums. The place for beryllium where they concentrate is mainly in a rock that we call pegmatites. And pegmatites basically serve as a rock, a magmatic rock, that incorporates a lot of incompatible elements. When you build minerals, you're always going to go for the easiest one first, things that fit together nicely. But not all elements fit together nicely. Some of them are really small, others are massive, and those are all concentrated in the pegmatites, left over till the very last, and then you build your minerals with it. So beryllium is one of those elements. So beryllium, you will often find it enriched in pegmatites, growing. That's why we find a lot of beryls in pegmatites. Now I mentioned that you need chromium to make it green, and chromium is also very rare, but it concentrates in completely different environments. It's usually associated with iron, vanadium, and other metallic elements. But I mean, this is a completely different environment than where you're going to find beryls. You would never have chromium enrichment in the pegmatites where you have beryl. So the real challenge, the real beauty of forming emeralds is when you bring those two extremities, those two extremely complex, extremely different environments, when you can bring those together, and when you bring those together, the result is going to be beautiful emeralds. So the first environment where this could happen is what we call pegmatite related. Very simply said, you have a rock where you have some chromium in there, and completely independent of it, you have a pegmatite intruding it. So your pegmatite provides your source of beryllium, your source of beryl, and that chromium that is present in the original host rock provides you with the green color. What kind of rock that is, the original host rock, there's a lot of variety there, but it's just, let's just say it's chromium rich. So at the reaction zone of those two, at the contact of those two rock types, you will form a third rock type, what we call a schist, but that is often very rich in phlogopite mica, but that is also where you will host the emeralds, because that is where your beryl comes in contact with your chromium and where those two can form emerald together. So I've just pulled up some sketches to go over that really quick. So in the beginning, you just have your rock with a little bit of chromium dispersed throughout it. This photo on the right can give you an idea of what this rock looks like. It can look very different as well, but now you have a sense of what it looks like. So you have this rock, and all of a sudden there's an intrusion happening, an intrusion of a pegmatite rich in beryllium. So this beryllium goes into this rock. So you can see that there's already some beryl crystallizing here, but it doesn't have that emerald color. Where you do get that emerald color is at that reaction zone. So when you get that pegmatite intrusion in that chromium-rich rock, you form that reaction zone where you form those beautiful beryls with some chromium from the host rock. So that's where you will form your emeralds, often associated with a lot of mica. This is one of those examples from the Malisheva Mariinsky mine in the Ural Mountains in Russia, where you can see this beautiful emerald crystal, but it's completely surrounded with phlogopite mica. And that is what we find in this reaction zone around the pegmatite, between the pegmatite and the host rock. This is a photo of what it looks like in real life. You have the white one, that is the pegmatite intrusion. You have the very dark one, that is your source of chromium. But you will have, here I've indicated where you have the reaction zone. So the reaction zone is between the red line and the white line. And that is where you will form the mica schists and where you will crystallize your emeralds, because that is where the beryllium and the chromium comes together. This is an example of what it looks like. This is a beautiful emerald crystal from Ethiopia, where you can see how closely related it is with those micas that are also growing in that contact zone. Now, of course, when you say it's they grow together, you often see those as inclusions. And everyone who has looked in a microscope at emeralds, especially those pegmatite-related emeralds, that means Zambia, Russia, Madagascar, Brazilian material, often sees these mica platelets because they grow all around it. They're completely covered with it, so they're dispersed throughout it. And something else I want to note here is that we often see a lot of fluid inclusions in emeralds, but the fluid inclusions that we see in this type of environment are fairly simple. They have these rectangular shapes. There's just this single bubble in there, which indicates us that there's no real complex fluid interactions going on. And I say this because the next type does have those complex fluid interactions. So that is the next type. I will simply call it Columbia type, because Columbia is the best example, and Columbia is a source that everyone is familiar with for emeralds. But we start out with a very different type of rock. We start with what we call shale rocks. A shale is a sedimentary rock, so it means we start with loose sediments and we start turning them into a rock. And basically we start out with clays. So they're very rich in clay minerals and quartz. There's often a lot of organic matter. So we still have that very black rock that you can see here. This is a photo actually taken in Colombia. Those white veins, you should ignore those, but that black, that really dark rock, that is that shale that we're talking about here. Now, if we look a little bit more emerald focused on this shale and look at the ingredients for our emeralds, we're looking for chromium and vanadium to make it green, but those are around 100 parts per million, so very rare. But the most important ingredient that we need to form our emeralds, to form those beryl crystals, is actually beryllium. And beryllium, there's only 4 to 5 parts per million. So there's a little bit more than the average, but almost nothing, almost neglectable. Now, thank God for us, something is happening with those rocks. There is a hydrothermal fluid that moves through those rocks. So what is a hydrothermal fluid? It's a fluid at higher temperatures. I think in the case of Colombia, it's 300 to 400 degrees. Because it is at that pressure, it doesn't boil, so it still behaves as a fluid, but it has a very high salinity. So there's like 35 to 40 weight% of it is dissolved salts. That's about 10 times as salty as seawater. But because it is that salty, it has the potential to leach out elements from rocks. So it basically has the potential to move past rocks and pick up certain elements from that rock, basically sucking them out and taking them into that fluid. Now let's go back to some sketches. So let's start out with the shale rock. The shale rock, mostly made up of clay. There's some organic material, and there's a little bit of chromium and beryllium sprinkled throughout. But it's not concentrated enough to actually grow those beryls, those emeralds in there. Now at a certain point, a lot of fluids are being pushed through that system. Whatever the reason for that fluid migration is, it is a lot of fluids. There's so much fluids that they're able to leach out those elements from the shale, which includes the beryllium, which includes the chromium. So the elements that we need to build those emeralds are gradually picked up by those fluids. And because there's so many fluids, there's so much of that that's left out. Now, of course, because there is such a push of fluids, because there is so much pressure being put on that system is going to start showing some cracks. So deep underground, that rock is not going to stay intact, and it's going to start forming fractures. Now, of course, there's still fluids moving through them. And when those fluids encounter fractures, your fluids will always follow the path of least resistance. Why force yourself very slowly through that rock if there are these fractures that are basically highways that you can follow? So a lot of these fluids go towards those fractures, and when they reach those fractures, they will basically dump all the elements that they're holding, crystallizing different minerals. Of course, we see a lot of common crystals, common minerals like calcite, like pyrite from the iron and the sulfur that are very common in these shales. But remember, there's also beryllium and chromium dissolved in those fluids. So those get deposited there as well. So those entire fractures, they get filled in with a whole variety of minerals, some feldspars, some carbonates, some quartzes, some pyrites, some other sulfides, but also your beryls with your chromium. And that is what we're really after. So eventually it will look like this. Here on the left, we see a beautiful example of a nice big emerald from Muzo, Colombia, associated with this white matrix, which is a carbonate. Maybe it's dolomite, maybe it's calcite, doesn't really matter. We also have that golden, very shiny mineral, which is pyrite, but we also have those black fragments, and those black fragments are the original shale rock in which those veins formed. Now on the right, we have a closer look at those veins where we have beautiful carbonates again with a lot of pyrite sprinkled, but also those beautiful emerald crystals that are crystallized in those veins. Now, of course, when we see that there is a lot of these fluids involved, very complex fluids, hydrothermal fluids, we also see that in the inclusion scenes. Colombian emeralds typically have these very irregular, jagged, three-phase fluid inclusions. And that is actually that hydrothermal fluid that was trapped when the emerald grew. So the emerald didn't grow at room temperature conditions. It grows at a higher temperature, it grows at a higher pressure, but right now they are at room temperature. So at room temperature, that hydrothermal fluid is not stable. It cannot hold all its minerals anymore, all its elemental content, everything that is dissolved in it, and it will crystallize those salts. And that salt is what we see in this little cube is halite. That is just basically salt from that hydrothermal fluid. Remember, hydrothermal fluid, 10 times as salty as seawater. That's just the salt that we see crystallizing from it. Plus the shape of it indicates that there's very complex hydrothermal fluids involved in this system. So just to recap for emerald geology is we need chromium and we need beryl. And basically for beryl, we need beryllium, and chromium and beryllium are very uncommon elements in the Earth's crust. And even when you find them, chances of finding them together are very, very uncommon. And that is what makes emerald geologically so special, because it's really the best of both worlds brought together, forming this magnificent gem. And the two environments where we most commonly see that is where we have a pegmatite, beryllium source intrusion in a chromium-rich rock. And where those two meet, we will form a reaction zone where our emeralds can grow with a beautiful green color because of the chromium, and the beryl because of the beryllium from the pegmatite. Now you also have another system from Colombia, where we, mainly Colombia, where we have hydrothermal fluids, a lot of them moving through a system, picking up those very rare elements, and then all of a sudden concentrating them in veins, where we deposit emeralds together with other minerals. So I think this gives you a little bit of an idea of the geology of some of the most common colored gemstones. And I just want to highlight that this is a very exciting but underexplored part of geology. Geology and ore forming processes have traditionally always focused on metals, on commodities, on minerals that have practical industrial use, which is sadly not really the case for gemstones. Plus, a lot of these systems are very complex, so you need a very good understanding of all aspects of how the Earth works, both physically, chemically, at high temperature, at low temperature, magmatic, sedimentary, metamorphic. You need to understand all these systems and be able to put all those pieces together to really reconstruct the geological history of most colored gemstones. Now, of course, we have the main challenge that most of the colored gemstones are found in secondary deposits. So there's no link with the geological formation. Even if we want to, it is very hard to trace those stones back to their original rock, which means that we have to rely on a very limited data set, mainly based on inclusions, to decipher their geological origins. I just want to highlight that in the last decade, we've seen enormous advances in our understanding of the geology of gem deposits. And that is mainly because a lot of academic groups have shown an increasing interest in geology of gemstone deposits. And GIA is playing a very active role in there by supporting research scientists at universities with samples, by collaborating with them, by having postdoc people work in GIA on these problems, on these challenges, to better understand the geology of those gemstones. And I just want to bring this one up as a last slide, that there's 3 main reference works on geology of gemstones if you really want to know more about it. A lot of this is very technical, but I think if you take your time, you can really get through it. And I think one of the most complete books is the Geology of Gem Deposits book, that I think was the 2nd edition, was released in 2014. Which has a very good explanation of a lot of gem deposits, including a lot of gems that I didn't discuss here. Then there's also the Geology of Gems, written by Mr. Kivlenko from Russia, which focuses a lot on gem deposits in the former Soviet Union. So a lot of gemstone deposits that are lesser known in Western communities, with a lot of, but a lot of research has been done on them by local scientists, and that research, you can find it in this book, Geology of Gems. And then in the last edition of Gems and Gemology, which was completely dedicated to geographic origin determination, there is also a full explanation there with a full article with the state-of-the-art understanding of corundum, ruby and sapphire, and emerald deposits worldwide, which is way more comprehensive than the introduction that I could give you today. So I think with this slide, I just want to say thank you all for joining. Thank you all for listening. Thank you for all staying, because I see that I've maybe overstepped a little bit time-wise, but I hope it was interesting for all of you and that most of you were able to catch a lot of it and understand a lot of it. And if you don't, I think right now is the time to ask some questions.
Yes, it is. And thank you so much. Thank you, Wim, because I know it's late where you are. It's about 1 a.m. where you are. And
that's okay.
You should feel like you're in good company, because we did get a few people saying that they would very much like a marble countertop with ruby in it as well. So,
well, yeah, maybe there's an opportunity for an entrepreneur there.
Exactly, exactly. So let's go ahead and jump into some of the questions. So is there a correlation between the type of rock, like igneous rock, and gemstones?
Yeah, well, of course, in different rock types, you crystallize different minerals, and those minerals could be gems, they could not be gems. So yes, in different rock types, you will find different minerals. A gem like topaz, for example, is almost always going to be associated with pegmatites, while other minerals can be found in a variety of host rocks. So yeah, understanding the rock types is very critical. Understanding which minerals form them is critical to understand which gems will form them. But the gems that we discussed here obviously show up in a variety of settings. So that's why I chose those to explain.
Okay, so for basaltic corundum, how can we know if it's been heat treated or not, since it's naturally been heated by the alkali basalt?
That is extremely challenging. That is one of the main challenges that we're facing, that the gemological community is facing right now, basically, because a lot of these those basaltic gemstones can be improved by heat treatment. They are routinely heat treated, so it is very difficult to detect that. But at GIA, we are doing a lot of our own studies where we are gradually heating and documenting those stones to see the subtle changes in inclusions while we're heating them, to see the subtle changes in spectroscopy. And I think if you go back to the talk that Dr. Aaron Paulke gave a few weeks back, he highlights some of these advanced techniques that we can use to detect heat treatment in all kinds of stones, but also in basaltic sapphires and rubies.
Okay, great. Can you explain why chromium gives a red color to corundum, but a green color to beryl?
The short explanation is it's in a different setting. So the crystal structure of aluminum and of beryl is very different. So the crystallographical position where your chromium is different, which means that it has a little bit of a different interaction with light, which is why it looks green in emerald, why it looks red in corundum, why it can look green and red in alexandrite. Because it has that different position in the crystal lattice, is surrounded by different atoms, so there's different interaction with light when light passes through it.
Great. What causes some silicate materials to form versus other species, even when all the necessary elements are available for both? So why do we see corundum in marble in Southeast Asia, but we don't see tanzanite in marble in Southeast Asia?
Well, first of all, I think tanzanite, it's very difficult to compare tanzanite with corundum. I think what I discussed now for corundum applies to corundum and corundum only. A case can be made to include spinel there, but comparing corundum and tanzanite, they're two very different minerals. They grow in very different conditions. So it's not really a valid comparison. That would be like comparing baseball to basketball. I mean, they're both sports. Tanzanite and corundum, they're both gems, but the rules are different, the conditions are different, the playing field is different. So it has its own specific set of ingredients to grow tanzanite and its own specific set of conditions, pressure, temperature, fluid compositions to grow tanzanite.
Okay. What is the difference between sulfides and sulfates?
Well, a sulfide just has sulfur, so a sulfide group, and while a sulfate has a sulfate group, which is basically SO4, so it has an oxidized sulfur in there.
So not all minerals are crystals. Can you go into that a little more and explain that in more depth?
Yeah, so for a crystal, you just need that ordered structure. While for a mineral, it has to be not biogenic, it has to be solid at room temperature. So a crystal is, and what I'm gonna say now is a bit debatable, but because ice is not a solid at room temperature, but you see ice crystals. Snow is a crystal, but it would not be considered a mineral because it is not stable at room temperature. But again, this is highly disputable between mineralogists. So there are, it is a bit of a loose definition, but those are the main characteristics. But for a crystal, you mainly need that ordered structure. Like you can get a sugar crystal, for example, but a sugar crystal is biogenic, so it cannot be a mineral because a mineral is not biogenic by definition, although it is a loose definition.
Okay, great. Okay, so this will be our last question. How can you tell that a corundum is formed near, in, or outside of a rock?
Well, when a corundum has been when a ruby or sapphire has been subjected to heat naturally, that heat has been applied in a very different way. So that is very gradual, sometimes over millions of years with very low gradients. While if you do it in a furnace, while it is done by people, it is really a shock. You heat it to very high temperatures, from a very low temperature to a very high temperature, in very quickly, which is what gives you different reactions of crystals. Because even if you heat it over the span over a month is nothing compared to 100,000 years. So we really heat stones in the blink of an eye compared to the way that nature does it. We go very fast up, we go very fast down, while nature takes hundreds of thousands of years. And that is how you can decipher most of the, that's where most of the differences come from.
Okay, great. Well, thanks again for joining us, and thanks for everyone that stuck around a little late. If you have any questions, please find us on Instagram, Facebook, LinkedIn, and Twitter, and who will break down our GIA research and how we use it to develop the curriculum we teach at GIA. So thanks everyone for joining.